Good morning, dear students. Today we are going to discuss about cycloaddition reactions. We know that cycloaddition reactions are intermolecular reactions, addition reactions. Here two olefinic compounds together react to get a cyclic product. And there are two new sigma bonds are formed and two pi bonds disappears. Examples for cycloaddition reactions are 2 plus 2 cycloaddition reaction and famous 4 plus 2 cycloaddition reaction, that is our Diels-Alder reaction. All these things are studied in previous video lecture. Now I am discussing about the mechanism of mechanism of cycloaddition reaction. It can be explained by FMO method proposed by Woodward and Hofmann. According to Woodward and Hofmann rule, feasibility of a cycloaddition reaction is determined by HOMO of one reactant and LUMO of other reactant. We know that in cycloaddition reactions there will be two reactants. They approach in parallel planes, not through same planes. So the reactants approach from two different planes, not in same plane. If consider this is orbital of one of the reactants, this is another component for cycloaddition reaction, and these are the terminal lobes. Here two reactants approach together from parallel planes, not from same plane. And if these two orbitals approach from same side, this is same side approach and this is same side approach. This type of addition is known as suprafacial addition. That is same side addition. And suprafacial addition causes sigma bond formation. If the orbitals approach opposite side, consider this is one of the reactant and this is another reactant, and this is supra addition, that is same side addition, and here the orbitals adds from opposite phase. This addition is known as antarafacial addition. So this is supra, this is supra. So it is called a supra-supra addition. This is supra, this is antarafacial addition. So it is called a supra-antara addition. So antara addition is opposite phase addition. And antara phase addition is geometrically forbidden. First, we have to discuss about 2 plus 2 cycloaddition reaction, in which first case is 2 plus 2 cycloaddition reaction in the presence of heat undergoing supra-supra addition to form cyclobutane. Here, according to Woodward-Hofmann rule, we know that HOMO of one reactant and LUMO of another reactant have to be considered. So, HOMO reactant molecules are ethylene. So the orbitals of ethylene molecules. Then HOMO of C2 system, which is HOMO. Psi1 is HOMO. So HOMO of C2 system, Psi1, and LUMO of C2 system, that is Psi2. Then mark the symmetry of the lobes. Psi1 means plus plus, Psi2 plus minus. Then in the presence of heat undergoing supra-supra addition, that is same phase addition. This is supra addition, this is supra addition. So this is supra-supra addition, same phase addition. Here plus and plus symmetry, here minus and plus symmetry. So here one sigma bond is bonding interaction, another sigma bond is anti-bonding interaction. Therefore, its symmetry forbidden. So 2 plus 2 cycloaddition reaction in the presence of heat undergoing supra-supra addition is symmetry forbidden. Consider the second case. 2 plus 2 cycloaddition reaction in the presence of heat undergoing supra-andara-facial addition for the formation of cyclobutane. Again, in the presence of heat, we have to consider HOMO of one reactant and LUMO of another reactant, C2 system. So, same situation as previous case, plus plus, plus minus, LUMO side 2, HOMO side 1. Then addition is supra-andara. Supra means same phase addition. Andara means opposite phase addition. This is opposite phase addition. So here plus plus symmetry. Here also plus plus symmetry. So here both the sigma bonds are bonding interactions. So its symmetry allows. But we know that Andara facial addition is geometrically forbidden. So, it's geometrically forbidden. That is the case of 2 plus 2 cycloaddition reaction in the presence of heat. Next case is 2 plus 2 cycloaddition reaction in the presence of light undergoing supra-supra addition. In the case of excited reactions, HOMO of excited molecule and LUMO of unexcited molecule determines the feasibility of a reaction. So, here we have to consider HOMO of excited molecule in the presence of light. So, C2 system, HOMO of excited system. HOMO of excited system will be side 2. HOMO of excited system will be side 2. Then LUMO of unexcited system, again side 2. LUMO of unexcited system, again side 2. Then symmetry will be plus minus, here also plus minus. Then following supra-supra addition, that is same phase addition, this is supra addition. So plus addition, minus addition, same symmetry. So its Symmetry allowed. Symmetry allowed. Both sigma bonds are bonding interaction. Then last case, 2 plus 2 cycloaddition in the presence of light undergoing supra-Andara addition. Same system, HOMO of excited system, that is side 2, LUMO of unexcited system, again side 2, supra-Andara addition, that is plus plus addition and plus minus addition, that is supra-Andara addition. So it is symmetrically forbidden. And supra-Andara addition geometrically forbidden. So this case is symmetrically forbidden and geometrically forbidden. Next cycloaddition reaction is famous Diels-Alder reaction, 4 plus 2 cycloaddition reaction. This is the reaction diene and dienophile interaction in the presence of heat undergoing supra-supra addition. So HOMO of one reactant and LUMO of another reactant. HOMO of one reactant in the case of C4 system, which is HOMO. Side 2 is HOMO. In the case of C2 system, side 2 is LUMO. We can select either 4 component or 2 component as HOMO and LUMO. Then what about its symmetry? Side 2 plus minus, here also plus minus. Then addition is supra-supra addition, same phase addition. What will be its sigma bonding formation? Here bonding interaction, here also bonding interaction. Both the sigma bonds are bonding interaction. So its symmetry allowed. So 4 plus 2 cycloaddition reaction thermally under supra-supra manner is symmetrically allowed. Then next case, 4 plus 2 cycloaddition reaction in the presence of heat undergoing supra-Andara facial addition. Same system, side 2 HOMO, side 2 is the LUMO of C2 system, plus minus supra-Andara facial. This is the supra-Andara facial addition. It is symmetrically forbidden because here only one sigma bond is bonding interaction, another sigma bond is anti-bonding interaction. And it is also geometrically forbidden since it is Andara facial addition. Next case is 4 plus 2 cycloaddition reaction in the presence of light undergoing supra-supra addition. Here we know that HOMO of excited reactant and LUMO of unexcited reactant. In the case of C4 system, which is HOMO in the presence of light, that is side 3 is HOMO in the presence of light, that is for excited, and in the presence of light for C2 system, side 2 is the LUMO, unexcited state. Then symmetry will be plus minus, here plus plus. First condition is supra-supra addition, that is same phase addition, plus plus minus plus. It is symmetrically forbidden. One sigma bond is bonding interaction, another sigma bond is anti-bonding interaction. Then last condition, 4 plus 2 cycloaddition reaction in the presence of light undergoing supra-Antara addition for the formation of cyclohexene. Same orbitals Psi3 and Psi2. Psi2 of C2 system and Psi3 of C4 system. Psi3, this is Psi2. This is HOMO and this is LUMO. This is for excited, this is for unexcited. Then supra-Antara facial addition. Supra, this is Antara facial addition. Here plus plus and here minus minus. So both the sigma bonds are bonding interaction. So it is symmetry allowed. But we know that supra-Antara facial addition is geometrically forbidden. So this is our selection rule or feasibility of cycloaddition reaction or mechanism of cycloaddition reaction proposed by Woodward and Hofmann. Here 4 plus 2 cycloaddition reaction, this is an example for 4 plus 2 cycloaddition reaction, that is Diels-Alder reaction. Thermally allowed addition is supra-supra, thermally forbidden supra-Antara, photochemically allowed addition is supra-Antara, photochemically forbidden is supra-supra. This is the case of 2 plus 2 cycloaddition reaction. This is an example for 2 plus 2 cycloaddition reaction, that is dimerization of ethylene. Here thermally allowed addition is supra-Antara and thermally forbidden is supra-supra. Photochemically allowed is supra-supra. Photochemically forbidden is supra-Antara. In short, we can say that 4 plus 2 cycloaddition reaction only takes place in the presence of heat. Here, because here only supra addition. We know that photochemically allowed addition is supra-Antara addition, but Antara addition is geometrically forbidden. So 4 plus 2 cycloaddition reaction takes place only in the presence of heat, and 2 plus 2 cycloaddition reaction takes place only in the presence of light. Here only supra-supra addition takes place. We know that thermally allowed addition is supra-Antara addition, but Antara addition is geometrically forbidden. So supra addition takes place only in the presence of light. So 2 plus 2 cycloaddition reaction only takes place in the presence of light, and 4 plus 2 cycloaddition takes place only in the presence of heat. That can be substantiated by Woodward and Hofmann rule. Next is sigmatropic rearrangement reaction. We know that it is intramolecular reaction, isomerization reaction. Examples for sigmatropic rearrangement reactions are 1,3 sigmatropic rearrangement, 1,5 sigmatropic rearrangement, 1,7 sigmatropic rearrangement, 3,3 sigmatropic rearrangement, Koch rearrangement, Claisen rearrangement, etc. belongs to the sigmatropic rearrangement reactions. Now we have to discuss about the mechanism of sigmatropic rearrangement reaction, that is again FMO method proposed by Woodward and Hofmann. Before entering to that, we have to discuss some more systems, pi-MO systems of C3 and C5 system. This is the pi-MO diagram of C3 system. Example for C3 system is allyl anion, allyl cation or allyl radical. All the three are examples for C3 system. Here the total number of pi electrons involved in the reaction is 4. Here 2 and here 3. Then this is the pi-MO diagrams of C3 system. Here one more orbital molecular orbital additionally come to the reaction, that is our non-bonding molecular orbital. We know that this is bonding molecular orbital and this is anti-bonding molecular orbital. And this is non-bonding molecular orbital. Non-bonding molecular orbital means orbital having same energy of the atomic orbitals. That is called a non-bonding molecular orbitals. This is bonding molecular orbital, this is non-bonding molecular orbital, and Psi3 is anti-bonding molecular orbital. Bonding molecular orbital having lesser energy than atomic orbital. Anti-bonding molecular orbitals having high energy than atomic orbital, whereas non-bonding molecular orbital has same energy of atomic orbital. And this dot represents non-bonding. Here the symmetry is plus 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 for Psi1, plus minus for Psi2, plus minus plus, that's for Psi3. Then consider the case of allyl anion, which will be HOMO, which will be LUMO. In the case of allyl anion, total number of electrons, pi electrons involved is 4. Psi1, this is Psi1, this is Psi2, this is Psi3. Then number of electrons 4. 4 electrons can situated in Psi1 and Psi2. So HOMO is Psi2, highest occupied molecular orbital. LUMO is Psi3 in the case of allyl anion. Then consider the case of allyl cation, which will be HOMO, which will be LUMO. In the case of cation, there will be 2 electrons involved in the reaction. So, 2 electrons in Psi1. So, HOMO is Psi1 and LUMO is Psi2. Then last case is allyl radical, which is HOMO, which is LUMO. In the case of allyl radical, 3 electrons are involved in the reaction. So, 2 electrons in Psi1 and 1 electron in Psi2. So, HOMO is Psi2 and LUMO is Psi3. So, this is the MO diagram, pi MO diagram of C3 system. What about vertical mirror plane symmetry and C2 axis of rotation of these molecular orbitals? For Psi1, in the case of vertical mirror plane, it will be symmetric, and Psi2 is anti-symmetric, Psi3 is symmetric. Then what is the case of C2 axis of rotation? In the case of Psi1, C2 axis of rotation is anti-symmetric, Psi2 is symmetric, Psi3 is anti-symmetric. And this is the pi MO diagram of C5 system. Example for C5 system is pentadienyl anion, pentadienyl cation, and this is pentadienyl radical. Here total number of pi electrons involved in the reaction in the case of pentadienyl anion will be 6. In the case of cation, it will be 4. In the case of radical, it will be 5. Then this is the MO diagram, Psi1, Psi2, Psi3, Psi4, Psi5. Again, this is non-bonding molecular orbital, and Psi1, all the symmetries are positive. In the case of Psi2, symmetry is plus plus, node minus minus. Then in the case of Psi3, plus node minus node plus. Then Psi4, plus minus node plus minus. Then Psi5, alternative plus and minus symmetry for all the 5 orbitals. This is the MO diagram for C5 system. Then in the case of electron filling, In the case of anion, which will be HOMO. Anion, total number of pi electrons involved is 6. So HOMO is Psi3, LUMO is Psi4. Then in the case of cation, total number of electrons involved in the reaction is 2. So HOMO will be Psi2 and LUMO will be Psi3. Then in the case of radical, total number of pi electrons involved in the reaction is 5. So HOMO will be Psi3, LUMO will be Psi4. This is the case of electronic arrangement for C5 system. Then what about vertical mirror plane symmetry and C2 axis of rotation? In the case of Psi1, vertical mirror plane is symmetry, Psi2 anti-symmetric, Psi3 symmetric, Psi4 anti-symmetric, Psi5 symmetric. Then what about C2 axis of rotation? In the case of Psi1 anti-symmetric, Psi2 symmetric, Psi3 anti-symmetric, Psi4 symmetric, Psi5 anti-symmetric. That's about C2 axis of rotation and C5 system. In the case of sigmatropic rearrangement reactions, there will be two type of migration. This is a representation of a system and this is one heteroatom, either X will be equal to hydrogen or any other group of atoms. So this atom or group of atom can migrated into third position or fifth position or seventh position according to their sigmatropic rearrangement reaction. So here if this atom migrate into same phase, it is called suprafacial migration. Suprafacial migration. Whereas if this atom migrates to opposite phase of this lobe, it is called antarafacial migration. So in the case of sigmatropic rearrangement reactions, there is two type of migration. One is suprafacial migration, another one is antarafacial migration. Suprafacial migration means same phase migration. Antarafacial migration means opposite phase migration. So let us discuss the mechanism of 1,3 hydrogen shift. And it can be explained by FMO method, that is Woodward-Hoffmann rule. Feasibility of a 1,3 hydrogen shift can be explained on the basis of HOMO of two radicals. How can you attain these two radicals from a single reactant? Here we consider the hydrogen shift or hydrogen migration from third position. So if there is a homolytic fission, it will result two radicals. One is H radical, another one is allyl radical. So HOMO of these two radicals have to be considered. That is the FMO method explained by Woodward and Hoffmann. So here this is our allyl radical, which is HOMO of allyl radical. From C3 system, pi MO diagram of C3 system, we know that Psi2 is the HOMO of C3 system. So Psi2, that is plus node minus, that is Psi2, that is our HOMO of C3 system, allyl radical, and this is our allyl, and here reactant, here is our hydrogen. This is our hydrogen. Hydrogen has spherically symmetrical orbital. So it can be represented by a sphere having positive symmetry. So this is the representation of a reactant. When it undergoes Suprafacial migration. First case is suprafacial migration. That is, hydrogen migrates to the same phase. That is suprafacial migration. This is plus minus. So here sigma bond formation is anti-bonding sigma bond formation. So that is unstable. So there is no bond formation and it is symmetry forbidden. It is symmetry forbidden. So 1,3 hydrogen shift in the presence of heat undergoing suprafacial migration is symmetry forbidden. Then what about antarafacial migration? Same system, side 2 plus node minus. We have to represent only terminal lobes. Then this is our hydrogen, spherically symmetric, positive symmetry, side 2. Then antarafacial migration. This is antarafacial migration. Antarafacial migration results sigma bond formation. Sigma bonding interaction and it is stable. So it is symmetrically allowed. It is symmetrically allowed. But we know that antarafacial migration is geometrically forbidden. Then third case, that is in the presence of light. 1,3 hydrogen shift under photochemical reaction following suprafacial migration. Here again HOMO of reactant have to be considered. In the presence of light, which will be HOMO? HOMO will be Psi3. Psi3 will be HOMO. So its symmetry will be plus minus plus. And this is our hydrogen having spherically symmetrical, positively symmetry. Then suprafacial migration. First case is suprafacial migration. This is suprafacial migration plus plus. It is symmetrically allowed. Sigma bond formation and it is symmetrically allowed. Then consider antarafacial migration. Antarafacial migration means opposite phase migration. That is plus system is same Psi3, that is HOMO. In the case of sigmatropic rearrangement reaction, we consider only HOMO. This is our hydrogen, and in the case of antarafacial migration, this is antarafacial migration. Plus minus, that is plus minus symmetrically forbidden. So 1,3 hydrogen shift in the presence of light by antarafacial migration is symmetrically forbidden and geometrically forbidden. Next is 3,3 sigmatropic rearrangement reaction. This is an example for 3,3 sigmatropic rearrangement reaction. That is our Cope rearrangement reaction. Here we this diene undergoes homolytic cleavage and converted into two allyl radicals. So first condition is thermal following suprafacial migration. That is, two allyl radicals react together to form the reactant for a 3,3 sigmatropic rearrangement reaction. Here this is the C3 system and which is HOMO. In the case of sigmatropic rearrangement reaction, we consider only HOMO of reactants. So side 2 is the HOMO of C3 system. This is also side 2. What is the symmetry? Side 2 plus minus. Here also plus minus. This is the symmetries of the reactant. First case is supra-supra addition. That is plus and minus. So both the bonding interactions, sigma bonds are bonding interactions. So here it is symmetry allowed. Symmetry allowed. Then what is the case of supra-antarafacial addition? Same system, side 2 is the HOMO. Here also side 2 is the HOMO. Plus minus. This is plus minus. Then supra-antarafacial migration. This is supra. This is antarafacial migration. Here one sigma bond is bonding interaction. Another sigma bond is anti-bonding interaction. So it is symmetry forbidden. Symmetry forbidden. This is the case of supra-antarafacial addition. Then third condition, in the presence of light. First one supra-suprafacial addition. Here HOMO of excited and HOMO of unexcited orbitals have to be considered. HOMO of excited. HOMO of excited means psi 3 is the HOMO of excited and HOMO of unexcited. HOMO of unexcited will be side 2. Side 2 is HOMO of unexcited. Here we have to consider HOMO of excited, which is HOMO of excited. Side 3 is the HOMO of excited. Then write the symmetries of orbitals. For side 3, plus terminal lobes will be plus. For side 2, terminal lobes will be plus minus. Then suprafacial addition, that is supra plus here minus. So it is symmetrically forbidden. One sigma bond is bonding interaction, another sigma bond is anti-bonding interaction. So it is symmetrically forbidden. Consider the last case in the presence of light. 3,3 sigmatropic rearrangement reaction in the presence of light undergoing supra-antarafacial addition. Here also the same system, HOMO of excited and HOMO of unexcited. Same system, that is side 2 and side 3 are the systems. Side 2 is HOMO of unexcited and side 3 is the HOMO of excited. So orbital symmetry will be plus, here plus minus. Then supra-antarafacial. This is supra addition. This is antarafacial addition. Supra-antarafacial addition is symmetrically allowed. Both the sigma bonds are bonding interaction. So it is symmetrically allowed. But we know that antarafacial addition is geometrically forbidden. So it is geometrically forbidden. That is the case of 3,3 sigmatropic rearrangement reaction. Same way we can draw the mechanism of 1,5 hydrogen shift, 1,7 hydrogen shift, etc. So this is the Woodward-Hoffmann rule for sigmatropic rearrangement reaction. This is 1,3 hydrogen shift that belongs to 4n system. Here the total number of electrons involved in the sigmatropic rearrangement reaction includes pi electrons and sigma electrons also. So 1,3 hydrogen shift belongs to 4n system and 4,7 system also belongs to 4n system. Thermally allowed migration is Antara, thermally forbidden supra, photochemically allowed supra, photochemically forbidden Antara migration. Then consider the 4n plus 2 system, which belongs 1,5 hydrogen shift and 3,3 sigmatropic rearrangement system. 3,3 sigmatropic rearrangement reaction, that is our Cope rearrangement and Claisen rearrangement. In the case of 1,5 hydrogen shift, thermally allowed migration is suprafacial migration, thermally forbidden is antarafacial. Photochemically allowed Antara, photochemically forbidden suprafacial migration. Similarly, 3,3 sigmatropic rearrangement reaction, thermally allowed addition is supra-supra, thermally forbidden is supra-antara, photochemically allowed is supra-antara, photochemically forbidden is supra-supra. This is feasibility of or mechanism of or selection rule of sigmatropic rearrangement reaction by FMO method. Hope it is clear. Thank you.